Hello everyone, my name is Witzany. Welcome to my talk, Action Angle Coordinates for Black Hole Geodesics and their use in EMRIs. So what will this talk be about? I will tell you about why should one do this? What are action angle variables? How do you construct them in Schwarzschild spacetime, in particular for Schwarzschild free test particle orbits, that is geodesics. And then I will briefly discuss what to do with these action angle coordinates in the future. So most of you who are watching this video at the LISA symposium probably know about extreme mass ratio inspirals, which are inspirals of stellar mass compact objects into massive black holes, such as those at the centers of galaxies. So you have, for instance, a neutron star, and it slowly inspirals into the central black hole. And the inspiral may span actually years in LISA band, and it happens in the millihertz, which is ideal for LISA. When you are treating these inspirals, theoretically, the zero order system that you use are geodesics, free test particle orbits, and then you use perturbation theory to build the inspiral to kind of gradually make the geodesic decay and fall into the central black hole. However, even geodesics themselves are quite complex. You know, you have a geodesic here on the left. So this is a geodesic in pure spacetime. And this makes it difficult for waveform actually generation, even because you need to generate many waveforms. It makes it complex for data analysis. So we have to use certain creative ideas, certain different approaches to see how efficiently we can actually generate waveforms. And my pitch here is that action angle coordinates will help to do that. And there are two reasons for that. First of them is that actions are gauge invariants, which means they set a certain golden standard for comparisons between the approaches to the relativistic two-body problem. And the second thing is quite obvious to someone who has been doing perturbation theory for EMRIs, is the fact that angles are essentially always referred to when constructing these perturbation theory approaches to extreme mass ratio inspirals. So they are very essential and they are often not known explicitly. And this work tries to go and construct them explicitly. Okay, so to motivate the angles and to kind of give you a first idea of what they are, consider a particle in a one-dimensional potential, just a Newtonian particle, conservative motion. So you have a conserved energy and you stay on isocontours of energy in some potential. So I chose a random potential here on the left. And let's say you move within this potential. And in the phase space, you have x on the horizontal axis, px on the vertical axis. And in the phase space, a motion near the minimum will make this sort of circle in there. And I want to parameterize the motion on this sort of circle by some sort of homogeneous phase. That's the idea of the angle. And then the action would kind of parameterize, the choice of the circle, let's say around the minimum. And the origins of this idea actually go all the way back to the beginnings of celestial mechanics. So when you parameterize the motion of planets in the solar system, you can use various geometric phases, along the ellipse, but it actually turns out these do not move homogeneously forward in time. So Kepler postulated a homogeneous phase, mean anomaly M, that actually moves forward in time homogeneously, and it fulfills this famous Kepler equation, which cannot be inverted exactly because it's a transcendental equation. And if you have ever dealt with celestial mechanics, you will probably know this equation. For us, I will just tell you that these coordinates are, the action angle coordinates are canonical, and they generalize this notion of a homogeneously moving phase forward to forward in time to generate integrable Hamiltonian systems. So how do you actually do this in a generic Hamiltonian system, right? So you go to the theory of generating functions, and you pick a generating function so that it generates, a transform to these action angle coordinates. And the equation that it has to fulfill is known as the Hamilton-Jacobi equation. You find solutions in principle, if you are lucky, which are parameterized by separation constants or by some constants, integration constants that parameterize the families of the solutions. And then you go through certain transformation steps. You have to compute these difficult integrals. And then in principle, if you compute them well, you can invert these functions and make a derivative of your Hamilton-Jacobi action, re-expressed in these new variables, or you just do it partially by inverting the Jacobian. And the extra hard part that typically one encounters when constructing action angle coordinates is that even though you have a transform to them, you don't have to transform from them. And the transform from them is actually more interesting because it gives you a closed form exact solution for the motion. So that's the basic construction, basic general construction that you have there. And I will now talk about how to do this in Schwarzschild spacetime, right? How to get all these steps in closed form in Schwarzschild spacetime. So you start with the Hamiltonian for Schwarzschild geodesics. You plug in the Hamilton-Jacobi action into this Hamiltonian. You plug in the derivatives of the S instead of momenta into the Hamiltonian. That's how the Hamilton-Jacobi action works. And you solve it, and a separable solution actually emerges. So this is the solution. You get an energy showing up in there as a separation constant, Lz. You also get total angular momentum as a separation constant, and you get these two slightly non-trivial functions in there. And they look like this. So the polar part, the theta part of the action is not that difficult to deal with. It is just trigonometric functions, but the R part is actually an elliptic integral. It can be expressed as an elliptic integral, which is a little bit annoying to deal with. And which, by the way, doesn't mean that, if you express it as an elliptic integral, doesn't mean that you have solved the problem, because we are not even talking, about this kind of inversions that one needs to do in order to get like useful action angle coordinates. So in order to do that, I have implemented this idea of essentially an eccentricity expansion in this paper, which is currently on arXiv. And the general idea is that you have, motion of circular orbits, you have some sort of effective potential, you have the centrifugal barrier and so on. And the generic eccentric motion actually can be seen as motion in this effective potential. And you perform a perturbative expansion and inversion in terms of deviations in energy away from this minimum of the effective potential. And you have a bookkeeping parameter kappa, which is essentially an expansion in eccentricity. It turns out to be equivalent to an expansion in eccentricity. I will not go through the technical details there. I will just tell you that to order eccentricity 10th, I have implemented this actually in a completely general spherically symmetric static spacetime. So take any modified gravity, find your spherically symmetric solution in there, and you can plug and play and get action angle coordinates in that spacetime here. You can test, Einstein gravity with, deviations of fundamental frequencies. It is all there, the tools, you can find it on my GitHub. But let's get back to Schwarzschild spacetime. How does this formalism work in Schwarzschild spacetime? You can parameterize your motion by these P and E. So P would be semilatus rectum in the Kepler problem. E would be eccentricity. They have formally the same expressions. You get exact expressions for energy and angular momentum, and you see that the energy has a certain reasonable behavior with P. So the smaller the P, the smaller generally the energy, because you are more and more bound to the black hole. But when you go with eccentricity to 1, you become unbound, so you reach energy 1 always. And also the radial action, which is one of the action angle coordinates, actually diverges when you have eccentricity 1, because your orbit is infinitely large in the radial extent. So in this parameterization, I took a look at the convergence, and it turns out when you do this eccentricity expansion to order 20, which can be done in Schwarzschild spacetime in particular, you don't get like necessarily too amazing convergence, because there is eccentricity, let's say 0.7, 0.8, where it seems very hard to sum enough terms to get convergence. But you can do a Pader summation, and then it seems to be, you just take 5 terms that you compute fully analytically, and you get sub-percent level precision everywhere in phase space. As just a sort of like proof of principle, you can also reconstruct exact orbits parameterized by coordinate time. And this is equivalent to sort of solving the Kepler equation, but I do it by the eccentricity expansion, and it works also for really quite eccentric orbits, really quite close to the black hole, more than Lisa will ever need, to be honest. Okay, I will just quickly sort of show all the information I have here. You can pause the recording and take another look. The idea for the use of these in EMRIs is to rewrite all your equations of motion in terms of action angle coordinates, transform the self-force terms and radiation terms, and then do a series of these near identity transforms that will make the equations of motion look much more practical. You also use action angle coordinates to kind of generate sources for the waveform and so on. And this should become very practical in the future. And that's all that I have time to say right now. And that's it. Thank you for watching, and email me any questions that you have or ask me in the Lisa Symposium website. Bye.